Now that we know what weak acids are and how to generally classify them, let's review how to approach equilibrium problems involving weak acid. And there's usually going to be two types. The first type is where you have to find the Ka value given some kind of equilibrium concentrations. And the second type is where you're given the Ka value and maybe some concentration, like an initial amount, but you have to use that information to find other equilibrium concentrations. And so again, the point of this entire portion of this lecture here is to stop yourself and make sure you understand a strategy. You have to use a strategy for chapter 13. We want to provide or produce a strategy for chapter 14, weak acid equilibrium problems as well. So for both types of problems, you're going to have a balanced equation. That means you're going to have your weak acid mixed with water in equilibrium to form H3O plus and the conjugate base. So we are dealing with conjugate acid-base pairs here, right? That's the type of equilibrium problems we're dealing with. And also, just to layer information, you might also be given the pH expression because you can get the H3O plus concentration from that. So if H3O plus is a part of our overall products, then we actually can use pH to find H3O plus concentration at equilibrium. If we're given, say, OH minus concentration or the POH, we can use that to find the OH minus concentration as well. Now, the pH expression for H3O plus, what are you getting at? Well, if these are our products, that means these are going to be considered our X value in a Rice table. So our X value is always going to be about the amount that's actually going to be reacting. In our head, the amount that's going to be reacting just means the amount of this weak acid that's going to dissociate. So if we find our X value, we have thus found our amount that's dissociating for our overall balance equation for a weak acid. Okay, folks? And that's going to be the same for both types of questions. Here's where it gets a little bit different. If you don't have a Ka value, you have to be searching for it, right? So there's not really any assumptions that you're looking at. You're going to be using your Rice table, substituting any expression that you can, whether you have the equilibrium amount for pH, for example, to solve for Ka. So a lot of people believe that these are a little bit easier. Even though you do have a Rice table, you have a way to get through to get that Ka value from its expression. Whereas the other type of problem, you won't be able to, you're not solving for Ka, you're actually given Ka. So if I'm given a Ka value, that means I actually can use my typical Ka assumptions that I saw in chapter 13. So if you have 10 to the negative 3 or higher, then of course, really 10 to the negative 3 or higher is what we're looking at. So 10 to the negative 4 or higher is going to be where you can make an assumption for your equilibrium reactions and equations and calculations. And then if you have 10 to the 4 or higher, not negative 4, just 10 to the 4, you also can make an assumption. So it's the same assumptions, just like chapter 13. For weak acid equilibrium, we get to add one more assumption. And that is, if we take our initial concentration of our weak acid and divide it by the Ka that's given, if that number is greater than 400, then we can make an assumption. So that's also an easier way as well. Sometimes with these problems, if I see a Ka value, I see an initial amount that I can get, I'm automatically going to divide it to see if I can make an assumption before even reading everything else. And again, you can do the vice versa of this. So if you take your initial amount of HA divided by your Ka value and it's less than 400, then you know you're going to be dealing with a quadratic equation or solving for squares, etc., etc. So as you can see, this is just priming your brain because we're about to go back to the Avengers compound to get some examples of this. We're going to get examples of both types of these problems. But I want to make sure you have some kind of way to organize yourself as you're getting through. So we have to have a balanced equation. You have to write the expression for Ka. Okay, and that's for both of these type of problems. You want to make sure you're defining X. What are you looking for in your Rice table? You want to make assumptions if you can. And if you can't make assumptions, go ahead and make them. You want to substitute any expressions that you can because you're going to be substituting for both of these types of problems. And then, of course, at the end, you can just solve for whatever you're looking for. And then you can go further and check those assumptions. So one way to check the assumption is by using this new little way to verify assumptions. And so this is what I want to tell you. If you only focus on this way to verify assumptions from chapter 13, add this new layer. If I see weak acids or weak bases, I can use this to my advantage. Of course, you can still use this either way. Either type of assumption you want to use, just make sure you know how to check it or understand how to actually utilize it. Now, what about notation? Notations are always going to be the same. Like if you have brackets, this means that you have a concentration at equilibrium, right? That's the same as chapter 13. Also, we know that water is auto-ionizable, so it has the ability to produce H3O plus and OH minus. But those numbers are so small that they end up being negligible, so we don't really focus on it, okay? Let's go ahead and get an example of each type of these problems. All right, we're back to the Avengers compound. And remember, this is the time that you're going to be creating and building strategies to approach these problems. If not, again, it's going to be more difficult for you as you go to the homework and then you go to the practice exam, et cetera, et cetera. So please just complete the problem with me now and then think of a way that you can approach it to make it easier for yourself. No matter what, the goal is to read the actual question, and then you want to gather all necessary expressions or equations, gather all necessary relationships, and then gather any necessary assumptions that you can use as well. So let's go ahead and do that. And then, of course, before I even start, don't forget what we just said in the previous portion of this part. We want to create a strategy for ourselves. So we know we've got to have a balanced chemical equation. We know we have to have a Ka value. We know we need to be using pH if it's given to us to find H3O+. Little details that's going to help us figure out how to approach them. So it says phenylacetic acid, C6H5CH2COOH, which we know definitely is an organic carboxylic weak acid, simplified here as HPAC, okay? That's how they're going to simplify it. Let me get another one here. HPAC. So far, nothing much has been said. It said that this HPAC builds up in the blood of persons with phenylketonuria, an inherited disorder that, if untreated, causes mental retardation and death. A study of the acid shows that the pH of this acid is equal to 2.62 when there is a 0.12 molar of the HPAC, okay? They want us to know what is the Ka value and what is the pKa value, given the information that we have here. So what do we must do first, folks? I write down everything I know. I'm writing down everything I see. Automatically, my brain is moving. I'm starting to think of relationships between pH, a relationship between how am I going to figure out what's disassociated here, all these little details. So here we have our balanced chemical equation. We have our HPAC, which they already gave us the abbreviation for here. And then I'm glad they wrote it this way as well, because we see the ionizable proton right there, right? So we have our H-class, we're going to mix it in water. It's going to be equilibrium because we're dealing with a weak acid. It's going to produce two things, H3O plus, or dissociate to produce H3O plus, and then the conjugate base, which means it does not have the proton. So we're going to go ahead and write our Ka expression for that, which is going to be our products divided by our reactants. We do not include water. And then we can set up a Rice table. Next, we have to go ahead and fill in our Rice table. So they gave us that we have a 0.21 molar of HPAC. This is not an equilibrium. They just gave us the amount that we started with and used in order to get the pH, okay? So that means we can put 0.12 molar as our initial amount for HVAC. Now for the pH, they did give us the pH of it, right? And so the pH is going to be when something's at equilibrium. And so if we wanted to use our pH to find the H3O plus concentration, we can say that H3O plus is equal to 10 raised to the power of negative pH. That'll get us that concentration there. And if I'm getting the H3O plus concentration at equilibrium, then that means I actually will be able to solve for my equilibrium amount of H3O plus here. Before we get there, let's go ahead and fill out the rest. So we're starting off with a 0 initial amounts for our H3O plus and our PAC minus, which is the conjugate base. Our change is going to be minus X. This is used up. And then we're going to have plus X here. And then we're going to have plus X here. Right, folks? Next, we're going to have our 0.12 molar minus X. This is going to be plus X here. And this is simply X. And this is also simply going to be X as well. So we have our equilibrium amount. That means if we were to plug this in, we say that we have X times X divided by 0.12 molar minus X. And you will automatically start thinking quadratic formula. But guess what, folks? Remember I told you that they gave us, or we can figure out the equilibrium amount of H3O plus. And if we know that equilibrium amount of H3O plus, we can use this equilibrium amount as our X value and substitute it for this X amount and this X amount to get any portion we want with our Rice table. So guess what? We have successfully bypassed quadratic equation once again. So how do we get our H3O plus concentration? We're going to take our H3O plus is equal to 10 raised to the power of the pH given, 2.62. And so our H3O plus concentration is going to be 2.4 times 10 to the negative 3 molar. That is our H3O plus concentration at equilibrium. And so that means I have to substitute that value as our X value. That is my X value at equilibrium. That means I can now use it as X. So this is going to be 2.4 times 10 to the negative 3 molar. This is going to be 2.4 times 10 to the negative 3 molar. And so when I actually have my X value, which is the amount dissociating, I automatically have my H3O plus concentration and my conjugate base concentration. Now we're going to subtract our 0.12 molar from our new X value, which is 2.4 times 10 to the negative 3 molar, and that'll give us our equilibrium amount of HPAC. Why do we need the equilibrium amount of HPAC? Well, guess what, folks? They want us to find the Ka. So if I just got this Ka value and this equilibrium expression and this equilibrium expression, I can solve this equilibrium expression and get the Ka value that we're looking for. And to get the pKa, we just take the negative log of it, and we'll get to that step next after I get a chance to erase all this. So where are we now? We're at the point where we use our pH, we use at our initial concentration and our pH up to help us build this rice table. We then use our pH to get our H3O plus concentration at equilibrium, which we found was 2.4 times 10 to the negative 3, which equals our X value. Now that X value is also equal to the conjugate base concentration, and we're going to use our X value to solve for equilibrium. So now I'm going to erase this so that I can solve for my equilibrium value for HPAC. All right, so I have now rearranged everything. I have my Ka expression up here. I know I have X times X divided by 0.12 molar minus X from all the equilibrium amounts that we see from our rice table. All I did is substitute our X value, which we already solved for, by getting the H3O plus concentration from the pH. So I plug everything in. 2.4 times 10 to the negative 3 times 2.4 times 10 to the negative 3 is equal to 5.76 times 10 to the negative 6. Divided by 0.112 minus 2.4 times 10 to the negative 3, which equals 0.1176 molar. So I divide these two numbers, and I get 4.9 times 10 to the negative 5. Okay? That is my Ka value. And we now have gotten one of our answers. The next thing I want us to do is get the pKa. So pKa is going to be negative log of my Ka value, and I get 4.31. So everything looks good. Again, we have to do a lot of work here to be able to start piecing out information. That's why it's imperative that if you have to go back to chapter 13 to review, you want to go do that. Because you need to know how to do equilibrium problems so you can layer in this weak acid equilibria information. Let's get into another example. So propanoic acid, CH3, CH2, COOH, again, another organic carboxylic acid, weak acid, which we simplify as HPR, okay, right here. If you simplify as HPR, is a carboxylic acid whose salts are used to retard mold growth in foods. What is the H3O plus concentration and the pH of a 0.10 molar HPR solution with the Ka value of 1.3 times 10 to the negative 5. So this time they want us to know and figure out the H3O plus concentration. We do not know the pH, so we're going to use the H3O plus concentration to help us, again, solve for pH. They give us an initial amount of HPR, and we're given the Ka value. So right off the bat, we could divide our initial amount given by Ka to see if it is greater than 400. If it is, we can assume and have any assumptions we have for Ka. Or we can use our old school assumptions from chapter 13, which is simply saying that if it's higher than negative 3, which we have as negative 5 here, then we also can make an assumption. So you can do either or. If I go ahead and take 0.1, divide that by my 1.3 times 10 to the negative 5, I get a very generous number, 7,692. And so that's way larger than 400. That means we definitely can be in assumption land here. And they've automatically simplified the weak acid to show the proton is going to be donated. And so we can go ahead straight away and get into our overall reaction for this, because that's pretty much the first thing we have to do. So you take your weak acid and you mix it with water. You know that this proton is going to be donated, Ronson-Lowry acid, right, to the oxygen. And so you're going to form H3O plus. What's left over is going to be PR minus. So if I was to get my Ka value, which I already know is 1.3 times 10 to the negative 5, now I'm going to add the expression that goes along with this number, and that is going to be my product, which is H3O plus, multiplied by PR minus, my conjugate base, divided by HPR. And that's what we see here, right? So now we have our balanced reaction. We have our Ka value. Let's go ahead and set up our rice table. How do I know I'm in rice table? Because guess what? We already have an additional amount that was given to us. They gave us 0.10 molar of HPR. And no matter what, because I am disassociating this proton, that's going to equal our initial amount. And how can we verify that? What we saw before when we first started our conversation about weak acids, that after dissociation, the amount of HA is equal to the amount initial. So because of that, whatever amount that is going to be disassociated is going to be equal to, or undissociated is going to be equal to our initial amount. So that's why we can use that as our initial amount here for our rice table. Okay, so I have my rice table filled out here. We know water is going to be a pure liquid, so we ignore that. We have our initial amount of HPR, 0.10 molar, and then our initial amounts of our products is 0. The change is just minus X. It's a one-to-one relationship for everything. And so we're producing plus X. Now our X value is going to be the amount that's undissociated, that's actually dissociated. Sorry, not undissociated. It's going to be the amount that's actually dissociated from this propanoic acid. And that's also going to equal to the amount of H3O plus and PR minus, which shows our X value here. Now we already said we can make an assumption, correct? So all we can do is basically get rid of this minus X that's added to our reactant here because we can make that assumption. And then we just want to move forward and start plugging in all of our values based on the equilibrium amounts and fill out the rice table like we normally would and complete the calculations like we normally would to solve for X. Once we have X, that's going to be our H3O plus concentration. Once we have the H3O plus concentration, we can solve for pH because they want us to get two answers here once again. So we know both of these are variables X, and then we also know that this is just 0.10 molar because we can neglect the minus X, right? So I have X squared divided by 0.10 molar is equal to our Ka value that was given, 1.3 times 10 to the negative 5. I'm going to cross multiply these two numbers, and then I get 1.3 times 10 to the negative 6. Then to isolate X and solve for X, I'm going to take the square root of both sides. So my X value is going to be 1.1 times 10 to the negative 3 molar. And so what does this represent? This 1.1 times 10 to the negative 3 is going to represent X, which also represents our H3O plus concentration, 1.1 times 10 to the negative 3. So we have effectively gotten at least one of our answers so far. So we've gotten the H3O plus concentration right here. Now let's get our pH value. Move it up here. Our pH value is going to equal to the negative log of 1.1 times 10 to the negative 3. And so our pH is going to be negative log times 1.1 times 10 to the negative 3 is equal to 2.96. So we have effectively gotten both the answers that this question wants. So again, these are very involved, right? But once you already know how to do equilibrium problems, all you're now adding in is making sure you have a balanced equation, making sure you know the Ka expression specifically for acid dissociation, and making sure you know how to plug and substitute things in. Okay? So that's why this becomes very important. Again, I recommend rewatching this video so that you can come up with your own strategy and you'll be able to approach these really quickly as you go along in practice, okay? You also can go further and get pOH. Remember, all those relationships we saw for pH, go ahead and get pOH. You can get the concentration of OH minus if you want, and so you can keep layering in. This is just an example of one question that is just strictly weak acid that you don't have to focus on pOH, they just want pH here.